Okay, so today we are happy to have Joseph Ayoub from the University of Zurich, and he will speak about the foliated topology and higher differential Galois theory.
Okay, great. So I hope everybody is hearing me well. Thank you very much for this opportunity to speak in this seminar. Right, so I want to speak about some old work of mine. It's now about at least 5 or 6 years old. And I have to say that since I've done this work, I haven't really been thinking too much about differential algebra. So I hope I won't be saying too many stupid things. And yeah, and also somehow one of the reasons why I kind of stopped doing this kind of stuff is because I am like I had an application in mind, and that application didn't work, and then I was not able somehow to find any other potential application. So in case somebody has some ideas or suggestions, I would be very happy to hear about possible application of this kind of stuff. And also probably some of these stuff have been like been known before, and so I'm also happy also to hear any kind of comments about yeah, what people think about these things. So right, so I want to start with some definitions, which are
Joseph, sorry for the interruption. Could you swipe your video away from the slide? So because at the moment,
what should I do?
At the moment you recorded 2 times, so it's if you can swipe it away from the screen.
So I didn't get what I should do. I should.
So at the lower right corner, there's a recording of whoever is speaking. Is it possible for you to swipe it away, like completely out of the yeah, okay, I think it's better now.
Okay,
thank you. Sorry,
no problem. Okay, thank you. Right, so yeah, I'm going to start with some definitions just to, so let's go this first part. So this will be about yeah, want to just to give yeah, some definition. I guess these are not really new, but just to make so that it becomes clear what I'm speaking about. So yeah, so maybe some reminders. So all right, so if we okay, let me fix from the start some base field k, which would be which will allow us to have characteristic 0. And so everything will be over this k. So if I start with x, say scheme over k. All right, so the foliation on, for me, a foliation on x will be simply is a map, is a surjective map, surjective morphism that goes from the sheaf of scalar differentials of x over k to some, yes, just like it's like a quotient, right? So to specify a quotient of the sheaf of differentials, and I give a notation for this. I write it x over f. Right. So this is the foliation is sorry. Right. So yeah, the foliation on x is this data exactly. So it's just a quotient of the sheaf of scalar differentials. Maybe I call this okay result name, and so such that so there's only one condition. So we want that. So what we can do whenever we have this natural maps called the RAM differentials that goes to lambda 2, omega 2, sorry, of x, which is by definition this is the exterior power of omega 1. Right, so this is the RAM differential. So on one hand, you have this quotient that is that you have given yourself. This that defines the foliation, and then that also give you a quotient from omega 2, right? So it's omega 2 of x modulo f, which is by definition again the exterior power. so the condition is that, that there should be a map morphism like this, which makes this commutative. That's the condition to be a foliation. And yeah, I forgot to say, but I mean, usually I would also assume that this omega-1 to be locally free. So let me put it also the definition. So usually it's assumed that this omega-1 XOR F is locally free of finite range. Right, so this is what is a foliation. Maybe a more standard definition would be to take a subsheaf of the tangent space, and I think this is what one finds maybe in differential geometry, but it's, of course, it's equivalent. Just one dualize and replace subsheaves by quotients. Right? Any question about this definition? Right. So if not, I mean, yeah, this is what I mean by a foliation. And so here's maybe a remark. So just for notation, so usually I denote foliation by symbols like this, x modulo f or y modulo g, etc. And so whenever I say, okay, let y over g be a foliation, I mean that I'm given myself a scheme, and then this quotient, this locally free quotient of the Keller differentials. Okay, just some terminology. Okay, right. Okay, so this is one remark. Let me give you some other remarks also, maybe more interesting here. So first remark is that the data, I mean the condition here that one can complete this square, that one can complete this, square by this map. This condition implies that actually one can define also the ramp complex of the foliation. So, right. So given the foliation, okay, foliation x modulo f, when one has the ramp complex, it has an associated ramp complex. That looks well. So it starts with the OX, and then you have this omega-1 XF, and then so yeah, I didn't say this, but so the fact that this map here is surjective implies that there is at most one possible map, like in this commutative. So the existence of this also implies that it's also unique, right? So one can maybe one can give a name to that. So it's called DF. Right. So you put here DF, and then so what I'm saying here is that you can complete this in a unique way to a whole ramp complex. All right. So you have this complex of sheaves on X, and in particular, you can speak about the ramp cohomology. So you can speak about the ramp cohomology of the foliation. That's one thing. Right, this is first remark. So there will be a few remarks. There is also so yeah, one way to think about foliation is to think about them as differential schemes, but without fixing the coordinates. So let me explain a bit how this works. So if you have, so assuming that omega-1 x mod f is actually free, not only locally free, but that it's free, and choosing a basis maybe omega 1 to omega n of big omega 1 xf. Right, so I assume it has rank n, and choose a basis of this locally, or this free module. Then so we can consider the dual basis. So let partial 1 up to partial n be the dual basis. And now, of course, I can view these guys as, okay, these are maps like this. And in particular, they give me, so since also, since this receives the sheaf of differentials, we get in this way derivations of OX, right? So we can view these guys as derivation OX. And in fact, they do commute, and the commutativity is precisely this condition that you can, again, let me go back to the definition. Oops. So the fact that you can fill in this square is precisely the condition that these derivation commute with themselves. So we have this commutator R0, and therefore we can view X. So X becomes in this way, becomes a delta scheme, where I take delta to be this set of delta to delta. Okay, and of course this can be reversed. So if you start with a delta scheme, you can, with a small condition, you can put you can define a foliation on your scheme. Okay. I hope this is clear. And let me see. Maybe I should write it, because this will be actually important later on. So maybe let's say conversely, given delta scheme, we can define K foliation. Let's call this scheme X. So and so I write this like this: X over AX, to say that, so it's a foliation which is associated to X, and where one take this to be just for X power delta. So that's it's OX and the dual plus. Right, and yeah, so here there's a small condition that one has to, a small warning, is that usually, so if you do this construction, then okay, you have this total derivation that gives you, by the universal property of the Galois differentials, a linear map like this. But this is not necessarily surjective in general. And so okay, then this will not somehow fill in, I mean, be a foliation in the sense I gave. But okay, so okay, so this is not surjective. This is not necessarily surjective. Okay, so but somehow in practice it is surjective. I mean, the most interesting case is this is always surjective, and then somehow, okay, modulo this, you will get a foliation. Otherwise, maybe not. But okay, so
Joseph,
yes.
sorry, just to clarify, by delta scheme here, you mean a scheme equipped with, such as the structure sheaf is equipped with n commuting derivations.
Exactly. Yeah, okay. And so the delta will be this set here. From, I mean, whenever I would say delta, essentially it will be this set, and delta scheme would be the scheme with n derivations that are commuted. And if you have something like this, you get essentially always a foliation by doing this construction, by taking omega AX to be the and the sum of n copies of OX. The only thing that you need to check is that you do have a surjection like this, but okay, this is not always satisfied, but somehow it's satisfied in almost all interesting cases. Okay. All right. Okay, so that's maybe second remark. And then third remark is that there is also a natural notion of a morphism between foliation. And that's as follows. So if you have two foliation, y over g and x over f, then a morphism between them, so something like this. So a morphism like this is simply a morphism of scheme. So this is called the underlying morphism. So it's just a morphism of scheme that satisfies the property, so such that the property that you want is the following. So again, it's a very natural property. So you start. So if you have a morphism of scheme, then you know that you can pull back the Kähler differentials on X, and then this will have a morphism to the Kähler differentials on Y. Right? And okay, on the other hand, you have this structure, where you have a surjection to omega 1 x over f, and also a surjection here. And so the condition is as before. So you want that you are capable of filling this square. And again, so if such a thing exists, it will be unique. Right. So this is what is the morphism operation. It's a morphism that has a property. Okay. So that was a long remark. Any question about this?
Okay. Yes, I have a question. So, just generally, where does this lead to? So you're thinking to talk about some higher differential Galois theory, right? So what are the problems that it, maybe some concrete problems it can address?
Right. So this, as I said at the beginning. So
I missed a few minutes at the beginning. Sorry.
Right. So okay. I mean, okay. Let me repeat this. So I was led to these kind of things for some application that I had in mind about 6 years ago. That application didn't work out, and so but I ended up somehow writing up this stuff, but then since I didn't have any application in mind, I somehow stopped working on that stuff. And yeah, so somehow it doesn't lead much to anything really up to now. And I was like hoping that maybe some of you would have some ideas on how to apply this kind of thing. I mean, as I will discuss today, I mean this. So this kind of language somehow leads to a natural notion, which is a notion of higher Galois differential groups that I think might be interesting. So maybe you will see this later. I mean, hopefully, I will have time to discuss this in some details. Okay,
Thank you.
Right. Okay, so. Right. So for the moment, this is just a definition. I want to say that it's a natural definition, and I'm not really claiming any originality. I mean, this is something that I think, in some sense, has been existent since a very long time ago. I mean, in differential geometry, the notion of foliation is precisely very close to what I'm writing here. So it's nothing really fancy or new. I mean, I'm not claiming anything very complicated, right? So it's just it's really the usual notion of foliation that you write down for schemes. That's all. Okay. Right. So these are some definition, and okay, let me make some remarks. So so this is a notion of morphism. You can use it to define. I mean, there is a natural definition of an etile morphism in this context. So I call this differentially etile just to make it a bit different from the usual notion. So if I have something from yg to xf, I say that this is differentially etile if the induced morphism from f upper star omega 1 xf to omega 1 yg is an isomorphism. And again, this is a very natural definition. If you know what is an etile morphism in algebraic geometry, this is essentially something like this. It's a morphism that induces an isomorphism on the Kähler functions. Okay. Right. So that's I should maybe have called this a definition. Actually, I don't know what's called. Sorry, it's a definition. Okay. And so that will be important for us later on. Maybe I should also make these kind of remarks. So right. So if you have X now, which is a smooth variety, smooth scheme, then you can associate to this a foliation, and I will call this the coarse foliation, and I would write it maybe there was C. This is a coarse foliation, and it's defined to be simply you take X and the whole sheaf of differentials, differentials. Right? This is an example of a foliation. So it's associated coarse foliation. But there's also, of course, another way to get a foliation is to take the zero sheaf, and this will be called the discrete foliation. And okay, let me remark the following also, that if you have a morphism of schemes, of smooth schemes, then f is etile in the usual sense if and only if the associated morphism on coarse foliation is differentially etile. So in some sense, this is kind of generalizing the notion of etile morphism. All right, so I guess I'm done with definition. Let me now tell you what is the Foliated topology.
Sorry, I have a quick question, if I may, Joseph.
Of course.
I'm going back to the definition of differentially etile morphism.
Right.
Just to clarify, you don't ask for the underlying morphism of schemes to be nice in any way at all.
No,
right?
no, really not.
Okay.
I mean, it can be anything. So for instance, I should also maybe add here. So any morphism of scheme gives a differentially etile morphism on the associated discrete foliation, for instance. Right. So because here the omega is 0, so of course any morphism will induce an isomorphism on the omegas. And right, so this is an example of a differentially etile morphism. Right. So yeah. Thank you for your question. Okay, so part 2. Okay, so Foliated topology. And again, I want to say that this is also a very natural thing to do here. If you start, I mean, if you know about the etile topology, you will see it's very analogous to what people, the way etile topology was defined. So okay, let me give some notation. So I'll call fol k. This will be the category of foliation. So I told you what is a foliation. I told you what is a morphism between them. So this form a category. So it's a category of k foliations. Okay, and so we define a topology on this category. So consider the Grothendieck topology. On foliation, defined as follow. So I'm just going to tell you what are the covers of this. So a family Fi, so I have some foliation Yi Gi going to, let's say, F, some index here. So a family is called is a cover, or is a foliated cover if so. Two conditions essentially. So the first one is I want these to be differentially étale. So and second is I want that the union of the Fi Yi to be equal to X. And I will not say really more, but this is actually not enough. So one has to be a bit more precise here. So let's say in a strong sense. So that, but let me not go into this because it's. But in particular, I don't want them, for example, to be flat or to be or to be, I don't know, of finite type or anything. So just some condition that ensure that somehow the union of the images is X, and each of the Fi's they have to be differentially étale. Right. So again, if you know what is the definition of the étale topology, it's very similar. For the étale topology, we also take a family of étale morphism, and we ask that the images cover the whole variety X. Okay, so that gives the foliated topology. Which I denote by or abbreviated by FT, like, yeah. All right, so and so, yeah, I mean, as I said, I was somehow working on some questions, and then somehow I thought that this could be useful, but somehow I wanted also to understand something. I mean, like the question that somehow was important for me at that time is the following: how to compute the cohomology, the étale cohomology of actually a course. So I started, one would start with a smooth variety X and view this as a foliation using this construction, the construction of the coarse foliation, and then start somehow covering this X with maybe non-trivial foliation, and then one would like to understand some of the cohomology of this this initial X. And so and A was actually something not completely arbitrary. So A was a discrete sheaf. So I will maybe not give a definition here now, but example, you could take, I don't know, GM, so the multiplicative group, and then view this as a discrete foliation, and then this will be some group object in the category of foliation, and it represents a discrete sheaf. So that would be an example. You could also take an abelian variety. And similar. Okay. So this was the question that I wanted somehow to understand, and that's the question that led to this higher somehow differential Galois groups. Right. Okay. So any question about this? So let me now get to the third part. So this will be the foliated homotopy type. Okay. And so this is a bit technical, and before maybe I speak about this, let me maybe first remind you about the more classical situation with the étale topology. So there is a very similar story in the setting of the étale topology that is very analogous to what I want to tell you about. So I start with the classical story. So okay, so it's a story which is due to Artin Maser and also Friedlander, and it's called the étale homotopy type of a scheme. So maybe I remind you of the construction. So this is due to Artin Maser. Okay, so once somehow, yeah. So once start with X scheme. Let's say maybe a finite type scheme over a field. That doesn't really matter. And so Artin and Maser, they associated to X an object that I will denote by H étale X, and this is called the étale homotopy type. Homotopy type of X. And so how this is defined, so I give you maybe not a very precise definition, but one that is almost okay. So what you do is you start with, so this will be, technically speaking, this will be a pro simplicial set. Okay, how is it obtained? So you start with, you take a cover, so let Y to X be an étale cover. You take an étale morphism, which is surjective. And then you look at, we consider the nerve, the Czech nerve, sorry. Of this cover. So what does it mean? So you start taking fiber product of Y with itself over X. So you look at that. And then triple. And then you have two obvious maps from the product to Y. First projection and second projection. You have the diagonal map. And here you have three maps, natural map, natural projections. And you have partial diagonals, and then that somehow continues. And this is a simplicial scheme. So that's that thing here. Okay, this is called the Czech nerve of the cover. Okay, there is always like an augmentation to X. Anyway, and then what you do, then you replace this complicated object by something simpler, namely you just look at the number of connected components in each degree. So you look at the pi zero in the naive sense, right? So the pi zero of a variety is just the number of connected components of this simplicial gadget. So I should put the dot. Right, so this is called Y dot. Okay, so that now becomes just a simplicial set, right? Simplicial set, and so a simplicial set is some kind of a homotopy type, and then so for instance it has. You can now speak about the fundamental group of this and so on. But of course now we see that right. So we made a choice here. So we took one cover, and of course I mean. We would like something which is intrinsic in X. So the idea is that you take all the covers now. So the homotopy, the étale homotopy type of X is really you do this construction, but for all covers. And that's why you get really a pro object, not just a simplicial set. All right, so that's essentially the construction of Artin Maser. So so the reason why this is interesting is that you get in this way somehow an invariant of your variety X, which somehow which contains a lot of information. For instance, it determines completely all the étale cohomology groups of X. It contains already, I mean, it contains also almost by definition the pro-étale fundamental group, the variety, and so on. Let me maybe just give an example. So the simplest example of that is you take the spectrum of a field. So your scheme X is just the spectrum of a field, and you can take for Y. So this is X, and you take for Y. You take the spectrum of an extension. Right. Let's take a Galois extension. Right, so if you run this construction in this situation, then we see that so this pi 0 of y dot is just something that can be written differently. It's the classifying. So as a simplicial set, it will be the classifying space of the Galois group of L over K. Right, so if you don't know what is the classifying space, so okay, let me tell you what it is. So if this is G, then this is again, this is a simplicial set that you get from G essentially. So in degree 0 you have a point, then you have G in degree 1. You have these two differentials, and then you have G times G in degree. So this is degree 1, this is degree 2, and here you have three maps which are given by the projections. So this is the projection to the first factor, projection to the second factor, and that's the multiplication map of G. And okay, so it's something that continues like this, and which is essentially, so what you need maybe to know is that you can recover completely the group with this multiplication out of this simplicial set. So it's a simplicial set that's essentially equivalent to the group, to the Galois group of L over K. And so if you run this construction, so from this, it's not difficult to see that, in fact, the étale homotopy type of spec K is just simply okay. It's the classifying space of the Galois group of K bar over K. Right. So it's again, it contains exactly the same information as the Galois group, as the absolute Galois group of K bar over K. That's an example. I need to do one remark before I can tell you about the foliated story. Okay, so here's a remark. So in fact, I was a bit cheating. So the construction of Artin Mazer, the thing that remind you about here. In fact, it's a bit more complicated. So one should not only look at Church nerves like this. One has to allow more complicated things, which are called hypercovers. I don't want really to get into the details. It's a bit technical, but hypercovers are somehow similar gadget. So they are also simplicial objects with an augmentation to X, but somehow they are a bit more complicated. So one does not just take a fiber product here. One would allow to cover this by something which is like a priori more complicated. So you could cover the fiber product, and then you can also cover this by other things. So you get things like that, which are a bit more complicated, which are a bit more general. Okay, so let me write this here. So one should really allow étale hypercovers of the variety X that we start with. And so this is, I mean, this is really, technically speaking, it's just a simplicial scheme that maps to X. And let me maybe write the first two conditions about this gadget. So you want Y0 to be surjective and étale. So it's an étale cover. and then you would like y1 again to be also surjective and étale now on the fiber product. Surjective and étale, and so on somehow. But it gets very quickly quite complicated. So you see already on y2. So y2, I want this to be a cover of something which is the following. So it's you take a fiber product of y1 with y1 over y0, and then this has a map. So okay, I'm not very precise here. You have to choose the so that there are three maps from y1 to y0, and you have to take the right combination here of the map. So but anyway, so there is something like this. You can build somehow some variety by taking fiber products of y1, y0, and x, and then you want the y2 to be surjective and étale on this, and so on. So this is what is a hypercover. And once you know what is a hypercover, then the right definition of the homotopy type of X is is as before. So you look at all hypercovers, and then you replace them by something simpler, like you look at that pi 0. But then of course you have to take them all. It's again it's a pro object. All right. Any question about this? So I see that I'm out of time already. Oh, I'm sorry.
Yeah, I mean, what was your plan? Kind of.
My plan is to let me give you at least the definition of this homotopy type, étale homotopy type, and then.
Yeah,
okay, I mean, I can try to finish in 5 minutes. Is it possible?
Okay, yeah, if you can try to wrap it up somehow, give an overview of the main remaining points in 5 minutes, that would be great. Yeah.
Okay, let me try to finish in 5 minutes. So okay, so here's the definition. So you do the same thing as before. So if you start with a foliation, then you define the foliated homotopy type of that object as before, essentially. So you look at okay, so maybe so I put a delta here because it's slightly different, and then so you take all hypercovers, but for the Foliated topology, and then you replace every gadget by something simpler, some kind of pi 0. But now pi 0 is not anymore a discrete set; it's a scheme already. So this is like okay, I should have defined this before, but since I don't have time, so given a foliation, there is a universal, some kind of a quotient map, where this here is a discrete foliation. Maybe I should start like this. So there is a scheme pi 0 yg such that if you use this as a discrete foliation, it receives a map like this, and it's kind of initial. So this somehow replace the connected component of a scheme in this setting. Okay, so this is a pro-simplicial scheme. Okay, and maybe let me state a theorem in an informal way. So the main theorem I wanted to discuss today is the following. So it works actually for a differential field. So we take K a differential field, so a delta field, and so the claim is that this foliated homotopy type of K is computable. So you can compute it, and okay, maybe I have to assume that the constant of K is an algebraically closed field. That's small, not so important here, but anyway, so it's computable. And in which sense? So you can say what is the pi 1 of that. So it's some kind of a homotopy type. So you can speak about the pi i's, and so the pi 1 is something that is not surprisingly, it's the Coltrane absolute Galois group of K. But then the interesting thing is that there are also some pi i's that are non-zero. I bigger than 2, so they are of course commutative, and so that they are commutative. That's of course it's clear because it's higher by I, but pro-algebraic group. So you get in this way some groups that you can actually even compute. So there are formula for that. Maybe I stop here. Okay, that was somehow essentially what I wanted to speak of. So
okay.
yeah,
great. Thank you, Joseph. Thanks so much for this very nice talk. So yeah, okay, let's thank Joseph. So are there any questions or comments? So please feel free to unmute yourself and just ask, or you can also ask in the chat if you prefer.
I have a question / comment. I was surprised to not see any niceness conditions on the underlying scheme morphism in the definition of differential et al. I'm wondering if you can speak to the choice to not impose flatness or something like that.
Okay, so yeah, right. So that's actually something which took me a while when I was working on this to get. I don't know if I can call it the right condition, but at least conditions that are good enough to develop this theory. So actually, I do put some conditions. So let me tell you what kind of condition I want to put on. So first, somehow there's an obvious finiteness condition. So if we think in terms of delta schemes instead of Foliations, maybe easier. So let's see if you have X delta scheme and you have Y to X morphism of delta scheme. So that essentially is something like a differential étal morphism, because here delta is the same, is fixed. So so this is an example of it, an étal. Now you can say when Y is a finite type over X, right? Meaning that so if these are affine schemes, so you have like a differential algebra. This is spec A, spec B. So you can say that B is generated by finitely many element as a delta algebra. That will not imply that as an algebra B is a finite type, but at least as a delta. So I put a condition like this on. No, actually I don't put a condition like this, and the reason why that is not good is that this is not stable by base change. So that would be some kind of a natural condition to put, but it's not stable under base change. So if you take another morphism like this, like for example, if you take a point, I mean, if you take something discrete, spectrum of K, but with the zero, right? So and you pull back, then this will not. I mean, for the pullback to be a finite type, that essentially the same thing as saying that as an algebra over K, it has to be a finite type, which is never the case in this setting. So it's not good to say that the morphism is a finite type, but somehow one has to replace this by something like okay. So here I use a theorem of Malgrange, which somehow tells you exactly how, or tells you that at least generically a morphism like this is not so bad on the level of algebras. That essentially it's Y is a finite type over X as a scheme, and then you have like some infinite dimensional vector bundle on Y. This is it's a theorem of Malgrange. I think it's called involutivity theorem. So okay, so we have some kind of a control on things like that, and so the conditions that I put is that I want this to be also true in general. So a family of differential étal morphism of Foliation is called is a cover if so first you want each of these Y I to X to be of this shape. So if you forget the foliation, I want yi to be essentially a vector bundle of infinite dimension over something which is a finite type and maybe not, yeah, a finite type over X. And that's somehow the essential condition. And then there is a condition, okay, which is much weaker than flatness somehow. But anyway, I don't know if I want to discuss it. But okay, there are some conditions somehow. But in the case, I mean, okay, I want to say that in the case where X is discrete, so the foliation is 0, then really any cover by finite type morphism is allowed. Like you can take an open subset, open subscheme, and its complement. This will be a cover in this topology. Okay, so
thank you.
Yeah, any other questions or comments? So maybe let me ask you. So you mentioned that those higher groups are commutative. Could you try to give some intuitive meaning or reason why? Like what's the meaning of this, or why does that come about? Or
okay, I mean the fact that they are commutative, this is not at all surprising. I mean this is a fact from topology. So the fundamental group, the pi I of a space for I bigger than 2, they are always commutative. That's a general fact from topology. So that's not really a surprise. What is surprising is that they are representable, but like they are really group schemes. Because a priori there would be like, you know, there's no reason for them to be representable by anything nice. Okay, so right, so what we can. So as I said, they are really computable. So I mean, the hard part is to show that they are representable. Once you know that they are representable by some nice variety, nice affine group schemes,
they're still pro-algebraic, though, right? I mean, they
are pro-algebraic.
Limits. Yeah. Okay.
So they are not affine actually. They are so pro-algebraic. So they are projective limit of. I mean, there is a big abelian part, you know, there. So they're not really affine. Maybe I said affine, but it's not affine. So anyway,
So just to clarify, so you mentioned the Colkin absolute differential Galois group. So it's the automorphism group of the compositum of all strongly normal extensions.
Yeah.
Okay.
So these are not really affine group scheme. They are really pro-algebraic groups. Right?
Yeah.
Right. So what I wanted to say, so you can show that, I mean, okay, for I bigger than 2, so this pi I, let's call it like this. So they are pro-algebraic, but really, I mean, okay, so I mean, at least like, okay, let's say, I mean, let me be a bit. I don't know, maybe in general, but at least if this is like a function field, I mean, maybe if you want, maybe just k with some variables, like so then this is really just so it's a big so it's like a big product of abelian varieties and extended by so there's an extension here by some big tori, big torus. And one can describe more or less explicitly what is the character group of this torus, and also, I mean, also somehow the character group of these abelian varieties. So in terms of the ramp homology, for instance, I mean, the torus part will be something like you take the hi, the ramp homology of of your field, and then essentially you tensor this with Gn. I mean, that's essentially the torus that you get here. And similarly for the abelian part, you get something like hi the ramp, a tensor the algebra of a dual maybe, and then so it's a tensor product over the endomorphism. And so here for a simple. So for every simple copy, for every simple abelian variety, there is somehow such a thing which appears in this Bible. And yeah, I mean, you can be very, very explicit about these pairs. You can compute them essentially completely in terms of the de Rham homology of your field.
So somehow all simple abelian varieties over the constants of K show up there.
Exactly, yeah. Everything shows up. Yeah.
All right. Okay. If there's no other questions, then let's thank Joseph again. All right. Yes, thanks. Thanks so much, Joseph. And yeah, I'm looking forward to seeing everyone next week.